Okay, so welcome to yet another lesson in linear algebra. Okay, so this is Math 2200, and last time we introduced what matrices are. Okay, so we talked about a number of things. We defined what matrices are, and then we talked about column matrices. We talked about row matrices. Okay, and then we also talked about the properties of these matrices. Okay, and the most important one of the properties, we say that the multiplication of these matrices is not what, is not commutative. Okay, meaning when you multiply matrix A with matrix B, this is never the same as matrix B multiplied by matrix what, A. So that's what we learned from the other lesson, the first class. Okay, so today we want to continue from where we ended. Okay, so I introduced what the transpose of a matrix is. Okay, so we are going to go deeper now. Okay, looking at what transposes are and their properties, and then we are also going to look at special matrices. Okay, so we have a lot of special matrices. So for today we'll look at these ones that I've listed here. Okay, we'll look at the square matrix, the equal matrix, diagonal matrix, the identity matrix, okay, the upper triangular matrix. We also have the lower triangular matrix, and finally we are going to talk about the trace of the what, of a matrix. Okay, so that's our roadmap for today's lesson. So we'll start uh, with the transpose there. Okay, so what did you say the transpose is? Okay, so we said the transpose is simply interchanging. Okay, we are interchanging the rows with the what, with the columns. Okay, so interchanging uh, rows with columns. That's what we call as the transpose of a matrix. Okay, rows and then let's say with columns here. So let me give an example here. So if for example you have a matrix A, okay, which is given by 2 4 1 0, okay, we said its matrix will just be the matrix in the form where we are interchanging these rows and these columns. Okay, so this first row here, okay, becomes a column here, so we are going to write 2 and 4. Okay, then this second row here becomes the second column, so we're going to write 1 and what, 0. Okay, so we see that this here is the transpose, so we've just interchanged the columns with the what, with the rows. Okay, so now we want to talk about some properties, okay, of this transpose of the matrix. Okay, so what are some of the properties or of the transpose of the matrix? Okay, so let's talk about those properties now. So we are going to say properties. Okay, properties of the transpose, okay, of a matrix. All right, so there are a number of them. There are about 5 of them, so we're going to talk about all of them. So the first one is that if you have the transpose of A plus B in the brackets like that, okay, this here is the same as you get the transpose of A and then you add it to the transpose of what, B. Okay, so if we have A plus B transpose, it's the same as A transpose plus B transpose. Okay, so that's the first property we are going to consider under what, transpose. Okay, and then the second one will be similar to this one and to just have a minus here. So A minus B transpose, okay, is the same as A transpose minus B transpose. Okay, so this is the second property under transposes. And then the important one now, okay, so if you have A and then you are multiplying it by B and then you say transpose here, okay, the answer that you are going to get here is not A transpose B transpose. Okay, so this here is wrong. Okay, so A AB transpose is the same as the commutative the commutated product of this matrix A and what and B. So we are going to say A multiplied by B transpose is the same as B transpose, okay, and then you write A transpose. So we see where this is coming from. Okay, so remember we said multiplication is not commutative, so AB, we said this here is not equal to what, to BA. So this property here, we can say that it's coming from here. So if I put a transpose there, okay, then uh the the other part here on the right hand side, it won't be direct, like just distributing this transpose to the A and then distribute it to the B. No. Okay, we are going to say that the transpose of AB, okay, is equals to the transpose of B multiplied by what, by the transpose of A. Okay, so the transpose of a product of matrices is not the product of the transposes, okay, but rather the commutated product of this transpose. Okay, so that's why we are going to be defining whatever we have here. Okay, I think I lost network and it kicked me out of the meeting. Okay, so I was explaining about the transpose. Okay, so we say the product here, the product of a matrix, okay, the transpose of the product of a matrix is not the product of the transposes, okay, but rather it is the commuted product of the transposes. So you see here I'm starting with A and then B, but on the other side we are going to have B and what, and A. Okay, so very important property, keep it in mind. You are going to be using it as we will be solving questions. Okay, and then the other one is that if I have A transpose, okay, so A transpose and then I transpose it again, I'm just going to go back to the original matrix, which is what, A. Okay, so these are the four properties, and then let me write one more here. Okay, so the fifth property we are going to say, so this is number 5. So the fifth property we are going to say that, okay, if I have a scalar k that is multiplying a matrix A, okay, so I have ka there where this k is a scalar, and then I transpose this, okay, the answer will just be equals to k and then A transpose. Okay, so when this transpose here goes to this scalar k, okay, it does nothing. Okay, so when you transpose a number, you nothing will happen. Okay, so for example this 5 here, okay, let me write here. So if I have this 5 here and then I find the transpose of 5, the transpose of 5 will be 5 itself. Okay, so it doesn't change anything. So if you have a scalar there k and then you apply this transpose to this k, it's just going to be what, k. Okay, and then this transpose you apply it to this A is going to be A transpose. Okay, so Ka transpose is equals to K multiplied by what, A transpose. Okay, so those are the 5 important properties when we talk about transposes. Okay, so any questions there? Any questions that you can have on those properties that I've explained there? Okay, no questions. I'll move forward. Okay, so now let's look at some special matrices. Okay, let's look at some special matrices. So we have a number of them, and we are going to talk about uh, each one of them. Okay, so special matrices. Okay, so we have a number of them. So the first one that we're going to talk about is a square matrix. Okay, so a square matrix, remember, I think I explained this last time. We said a square matrix is just a matrix that has the same number of what? Rows and columns. Okay, so a matrix that has the same number of rows and columns is called a square matrix. So I've just written in short form here, square matrix. Okay, so meaning, for example, if you have a matrix in this form, and then CD, this here is a square matrix because we can see two rows and two columns. Okay, all right, so that's it about the square matrix. And then we can also look at this special matrix known as okay, we can also look at this special matrix known as equal matrix. Okay, so equal matrices have to be identical. Okay, everything about them has to be identical. So if they say this matrix is equal to this matrix, okay, then it means everything about those two matrices is the same. Okay, so for example, you can have 1, 2, maybe 3 and 4 here as my first matrix, and then they say maybe this one is equal to I, J, K, and then L. Okay, and then they can ask you to find the value of I, J, K, and L. So by the nature that these two matrices here are equal, it means they have the same entries and they are of the same what? Order. Okay, so two things. They have to be of the same order and they have to contain the same entries. Okay, so we are just going to say our I there will be 1, our J will be 3, our K will be 2, and then our L will be what? 4. Okay, so these are equal matrix. So equal matrix should have the same entries and should also have the same order. Okay, should have the same order. Okay, so now let's look at a diagonal matrix. Okay, let's look at a diagonal matrix. So we're just going through the special types of matrices that we have. So diagonal matrix. Okay, so diagonal matrix, remember I said when we have a square matrix, something like this. Okay, when we have a square matrix, we said the entries that are going to be in this line here that I've drawn, okay, are going to be in the what? Main diagonal. So what is a diagonal matrix? Okay, so a diagonal matrix, okay, first of all it has to be a square matrix. Okay, so a square matrix is said to be diagonal if all the entries of the main diagonal if all the entries of the main diagonal are 0. Okay, so for example, let me say I have 1 here and then 2 there, and then here 0, even there 0. Okay, so this one here is a diagonal matrix because all the entries of this main diagonal here are what? Are 0. So let me give another example. So let's say we have this big matrix, so A 0 0, and then 0 B 0, and then we have 0 0 C. Okay, so we see that even this guy here is going to be a diagonal matrix. Why? Because all the entries of this main diagonal here, okay, are 0. So we can see 0 0 0 0 0 0. Okay, all right, so what if I write this matrix here? If I write 0 0 0 0, okay, so is this matrix here a diagonal matrix? Hello, is this matrix here a diagonal matrix? Anyone who can try? What do you think? Okay, so yes. Okay, so the answer is yes, it's still a diagonal matrix. Okay, because all the entries of the main diagonal are still zeros. Okay, so the definition doesn't specify, okay, Okay, it doesn't specify what numbers are you need to have in this main diagonal here. Okay, so even if you have zeros in the main diagonal, as long as the elements of this main diagonal are zeros, then we say that that matrix is a diagonal matrix. Okay, so there is a special representation that we can use to represent a diagonal matrix. Okay, so I'm going to give you that representation here. Okay, so let's say for example we had that matrix that I drew there. Okay, so we have A, we have 0 0, and then we have 0 B, 0 0 0 C. Okay, so let's say this is our diagonal matrix here, and then let's name this as matrix A. Okay, so you can simply express a diagonal matrix by just writing this form. Okay, so we are going to write A is a diagonal matrix, okay, which is equals to, and then you just write the entries of the main diagonal. So the entries of the main diagonal will be A, B, and then C, like that. Okay, so you can see that this is here is much easier to write this than all this that we have here. Okay, so we can represent a diagonal matrix, this guy here, in this form here. Okay, so in case you see diagonal and then you just have a matrix like that, just know that that is a diagonal matrix. Okay, and then you can write it in full from there. Okay, just know that it's a diagonal matrix and then you can write it in full from there. Okay, so an example I would give is this. Let's say we have such a matrix here. Okay, so let's say I have A equals to diagonal matrix, okay, that has 6 3 7. Okay, and then they ask you to write this diagonal matrix in full. So what are you going to do? Okay, what are you going to do? You're just going to say, okay, this is equals to, okay, so this here will be the first entry. I'll write 6, then 0 0. Okay, and then in the second row here I'm going to put the 3 here, and then these other places 0. Okay, the third row it will be 0 0 7. Okay, so we see that from the diagonal form of a matrix, okay, we can come up with the what, a complete form of a matrix. Okay, so sometimes they just give you matrix A is equals to diagonal, they give you the entries there, matrix B is equals to the diagonal, they give you the entries, and then they ask you questions from there. So they can ask you to find maybe AB. Okay, so for example, if we have another matrix B here which is diagonal, and then they say maybe 3 0 and then 2. Okay, so it means you can write the complete form of this, you also write the complete form of this, and then you just multiply those two matrices. Okay, you just multiply those two matrices. Okay, and then when we talk about these diagonal matrices, okay, they will be very important for us when we are finding the powers of a matrix. Okay, so they can ask you to find a to the power 10. Okay, so now imagine this means you multiply matrix A 10 times. Okay, so you can't manage. Okay, it will be very tedious for you to do that. So we are going to be using these special matrices which are called diagonal matrices to find what, A to the power 10. Okay, so any matrix that you are given and then they ask you to find that matrix to a certain power. Okay, first you have to express that matrix in diagonal form. Okay, and then from the diagonal form it will be very easy for you to apply this power 10 here. Okay, so we are going to learn that as we move in this course. All right, so that's a diagonal matrix. It has some special characteristics that you have to know. All right, and then the next one is the identity matrix. Okay, so the identity matrix acts as a 1 when we talk about matrices. Okay, so I'm going to say identity. Okay, so identity matrix so identity matrix like that. Okay, so what is what is an identity matrix? Okay, so an identity matrix, you can say, um, is a matrix, okay, whose diagonal entries are all ones. Okay, so remember, remember we're from talking about the diagonal matrix where we said we can have 2, 3, 4 there, and then the rest here the rest of the positions here we have zeros like that. Okay, remember we said this was a diagonal matrix. Okay, so this identity matrix now is just an extension of what these diagonal matrices are. So an identity matrix, okay, is simply a matrix whose diagonal entries are ones. Okay, so this here has to be a 1, this here has to be a 1, even this one here has to be a 1. Then we call that as a diagonal matrix. So for example, we can write 1 0 0 0 1 0 0 0 1. Okay, so this here will be called an identity matrix because all the entries in this diagonal here are what? Ones. Okay, so it's like an identity matrix, a special type of diagonal matrix, right? Where all the entries in the diagonal matrix are what? Are 1. Okay, so this identity matrix here is very special when we talk about matrices because it acts as a 1. Okay, so when you get any matrix and then you multiply it by the identity matrix, okay, you are just going to get the matrix itself. Okay, you're just going to get the matrix itself. So for example, if I have my matrix, okay, as let's say 4 1 2 and then 0 there. Okay, okay, so let's continue. So if for example I have this matrix A that has 4 1 2 0 there, okay, and then I multiply this matrix here by the identity matrix. Okay, so the identity matrix should be of the same order as the matrix that you are given. So the identity matrix for a 2 by 2 will just be 1 0 0 1. Okay, so if you multiply this matrix here by the identity, you should always, okay, you should always get the same matrix. Okay, so this identity matrix just simply a 1 of the um, the matrices. Okay, so if you multiply A, okay, a we multiply this A here with the identity matrix. Okay, we are supposed to get back the matrix what? A. So we're just going to get 4 1 2 0. Okay, and this is the case whenever we multiply by what? A diagonal matrix. We multiply by the identity. Okay, so in this course they usually write it in this form, so it's going to help us prove a lot of theories. Okay, so we can write that matrix A multiplied by the identity is the same as the identity multiplied by A, which is just the same as matrix what? A. Okay, so this here has to hold. So this identity is just a 1 of the matrices. Okay, all right, so let's now talk about the inverse matrix. Okay, let's talk about the inverse matrix after talking about the identity. Okay, so what is the inverse matrix here? Okay, so let's say we have a matrix A, which is a square matrix. Okay, and if B is another matrix, okay, of the same size as this A, such that, okay, such that when I multiply A with B, okay, I get the same answer as when I multiply B with A. Okay, and then this here will just give me an identity matrix. Okay, then say then we say that this matrix A here is invertible. Okay, we say that that matrix A is invertible and B is its inverse. Okay, so if we have this matrix A here and then we have another matrix B, okay, such that when we multiply A multiplied by B, we get the identity matrix. Again, when we multiply B multiplied by A, we get the identity matrix. Okay, then this first matrix A is said to be invertible. Okay, and then this B here is called the what? The inverse. Okay, so if you multiply any matrix with its inverse, you are supposed to get the what? The identity. Okay, so it's the same when you are considering the set of numbers. Okay, so when I multiply 2, okay, when I multiply 2 by its reciprocal here, I always get 1, and we know that 1 is an identity element, because when you multiply any number by 1, you still get that same number. Okay, so this means that this guy here, the reciprocal, is the inverse of what? These 2 here. Okay, so it's the same thing with matrices. If you have 2 matrices and then you multiply them, they are giving you the identity, then we say that that matrix there has a what? An inverse. Okay, otherwise if a matrix does not have an inverse, then we say that that matrix is singular. Okay, we say that that matrix is singular. So a singular matrix is simply a matrix that does not have what? An inverse. All right, so those are some of the special matrices that we have talked about. And then do I have more to talk about? Okay, yes. So just on the inverse there, we know that if this is my matrix A, then its inverse, A inverse, is given by, okay, so we go back to grade 12 where we say 1 over the determinant, and then we are multiplying by the what? The adjoint of that matrix A. Okay, so the adjoint of that matrix what? A. Right, so this here is the formula that you are going to be using when you are finding the determinant, I mean the inverse of a matrix. Okay, we're going to be using this formula here. Alright, and then now we can talk about the upper triangular and the lower triangular matrix. Okay, so lower triangular, it means in your matrix somewhere, okay, we can see a triangle that is formed. Okay, so I'll start with the lower triangular matrix here. So lower triangular matrix, okay, so this lower triangular matrix is a square matrix, okay, with all entries above the main diagonal. I mean above the, okay, above the main diagonal, okay, equal to 0. That's a lower triangular matrix. So let me write an example here. So if I have A here, and then 0 0, and then I have D there, and then here let's say B 0, okay, and then at the end there I have C, and then F, and then E there. Okay, so we see that in this matrix that I've drawn there, okay, all the entries above this main diagonal, this is the main diagonal here. Okay, so all the entries above this main diagonal here, we see that they are zeros. Okay, we have 0 0 0. So if you have such a matrix where all the elements or the entries above the main diagonal are zeros, then we call that matrix as a what? A lower triangular matrix. Okay, so we are going to be using this lower triangular matrix and the upper triangular matrix when we will talk about when we'll be talking about the row echelon forms. Okay, when we want to put a certain matrix in row echelon form, okay, we'll just be using this concept, the lower triangular matrix and the upper. So now let's talk about the upper triangular matrix. Okay, so the upper triangular matrix is like the opposite of what we are seeing there. Okay, so here we had all the entries above the main diagonal being 0, but here we have all the entries below the main diagonal being 0. So we can have A, B, C there, okay, and then this will be 0, and then we can say this is E, D, okay, and then we have 0, 0, and then F. Okay, so in this matrix we can see that this is the main diagonal here. Okay, so all the entries below, okay, all the entries below the main diagonal, okay, are zeros, so it's called the upper triangular matrix. Okay, so another way you can look at this is that, okay, when you go to the lower triangular matrix, it means this lower part here, starting from the main diagonal, coming like that and then going that, they are forming a triangle. You can see that triangle in blue. Okay, so this triangle is on the lower part of this matrix. Okay, so it's a lower triangular. And then when you talk about the upper, you can see that we have a triangle on the upper end. Okay, on the upper end there we have a triangle there, so that's the upper triangular matrix. Okay, so those are two special matrices. We shall use them when we talk about the row echelon form, especially this upper triangular matrix. Okay, when we want to express any matrix in row echelon form, we will be just be putting in what, in upper triangular matrix form. Okay, so those are the special triangles that we can talk about. Okay, and then let me also talk about the trace of a matrix. Okay, so the trace of a matrix will be the last thing I talk about in this lesson. Okay, so let's talk about the trace of a matrix. So trace, so what is the trace of a matrix? Okay, so the trace of the matrix is very simple, guys. Okay, so the trace of a matrix is defined as the sum of the entries on the main diagonal. Okay, so if I have A is equals to this matrix here, which is given by -1, maybe 2 there, I have 7, 3, and 5, and then I have -5. Okay, and then let's say 1, 2, maybe 7 there. Okay, so the trace of a matrix is just the sum of the entries in the main diagonal. So you're going to go in your main diagonal, which is this guy, okay, and then you're just going to add those numbers. That will be the trace. So it is represented as small letter t, small letter r. Okay, so trace of the matrix A, it is represented like this, is just equals to the summation of the entries in the main diagonal. So you have 1 plus, and then you have 5 plus, and then 7. Okay, so when we add that, what do we get? We get 11. Okay, so the trace of the matrix is just the sum of the entries in the main diagonal. Okay, and then one thing that you should note about the trace of the matrix, okay, is that when you find the transpose of this matrix A here, the trace of the matrix does not change. Okay, so let's find the transpose of A. So if I find the transpose of A here, it's going to be -1, 2, 7, and then I have 3, 5, -5, and then I have 1, 2, 7. Okay, so you see that the entries in the main diagonal there will not change. Okay, we'll still have the -1, the 5, and the 7. Okay, so very important concept there. Okay, so the trace of a matrix A is equal to the trace of the transpose of the matrix. So the trace doesn't change even if you find the transpose. Okay, so we can talk about those special type of matrices for now. Okay, we can talk about those special type of matrices. All right, so any questions on whatever I've explained here, guys? Any questions? Okay, so if there are no questions, then we end here for today's lesson. Okay, we continue the lessons tomorrow. So thank you so much for attending.